Sir. Hello. Balaji sir, shall we start, sir? Hello. Balaji sir.
Bhargav, can you hear me?
Yes, yes, sir. Shall we start, sir?
We can start. I have no problem.
Okay, sir. Yes. Good evening, dear participants. Again, today it's my privilege to introduce my guru, Dr. P.S. Balaji, for his second session in this ATAL FDP. So, as we have already introduced Dr. P.S. Balaji as he is an assistant professor from NIT Rourkela and is a great researcher. So, sir is going to take session on AML applications in condition monitoring of industrial components. So, I hope this will be an enlightening session for all of us.
Bhargav, I think your network is down. But anyway, can I start?
Yes, sir. Yes, sir.
Okay, I'm starting.
Yes, sir.
I'm pressing now. Is my screen visible?
No, no, sir.
Okay, so let me start.
Yes, sir. Now it is visible.
Yeah. Okay. Good evening, everyone. It's my pleasure to give my second presentation in this workshop. So, in the first presentation, we saw about AI and ML applications in additive manufacturing, and what are the rather than AI ML, we were focusing more on what are the advancements that came in additive manufacturing. But in this particular presentation, we will be focusing on AI ML application in condition monitoring of industrial components. So this particular field is very much highly relevant to my current research area, because majorly my research area is vibration control, and I am also working on drone technology. So I have my own company also. So I am also CEO of my company, which is Mechatecture Innovations. So now, as our topic is about condition monitoring, we should start from understanding what is condition monitoring. Before even we are going into condition monitoring, one thing is very clear, or one thing we need to understand very clear is this particular concept called condition monitoring will never die in any industry. What is the meaning of will never die in any industry? Say, for example, uh, before some years of time, the photographs were taken on the rolls. But later, when digital cameras came, the roll technology got eroded, which means the Kodak company have no more business possible because everything now converted to digital. So in some field, due to the development of technology, such some fields will die. But this particular field will never die. As long as a machine is running in an industry, this field will never die, only it will evolve. Okay, so such a very important field, and it's like forever field. So it has lot of opportunity for development, lot of opportunity to contribute, lot of opportunity to work. So with this great opportunity, let's also understand this topic and where you can actually contribute. In fact, I like to add one more examples before we start it. We are from Rourkela. There is a Rourkela steel plant that is next to our campus. We have Rourkela steel plant is part of a sale. So in Rourkela steel plant, they are having a conveyor belt, okay, that is carrying a coal. Certain point of time, what happens? The conveyor belt fails. Even if the entire Rourkela steel plant stops for one day due to the main conveyor belt failure, they will be incurring losses in crores, not even in lakhs. So they don't want to stop the machine even for 1 minute or even for 1 second. So in that case, they cannot take a risk of the failure of bearings for a conveyor belt or the belt gets failure. So they wanted to always measure and prevent any failure that comes into play. Okay. So this project is even given to us for doing the condition monitoring of such a mechanical components. So why I'm saying you this is this field never dies. This field will exist as long as any industry that is keep running in your area. Okay, and this is not even industry specific. It's not that it is only applicable to mechanical industries. No, even chemical industry, mechanical industry, biomedical, any kind of industry where there is a mission and which is must, this field is needed. So what is this condition monitoring? As the name suggests, it is monitoring the condition. Okay, it is a process of measuring and analyzing the parameters of the machinery or components to detect the change that indicate developing faults or degradation. Okay, so what is the goal? Why we are doing it? It's very simple. We wanted to detect the problem before it become a big problem. Anything in small, it is easy to solve. So we wanted to detect it much before it actually results in a bigger problem. And if I find a problem, I can schedule the maintenance and also I can avoid unplanned downtime. See, this downtime is highly should be avoidable thing by any industry. No industry loves to do downtime. They always wants to keep the machine running. So this is very important. Okay. Why condition monitoring matters? The goal is clear. So matters is also very similar. The first is it has to reduce downtime. So by detecting the failure early, I can rectify it when the failure is small. So I don't have to shut down the system for a long time. So by that, I'm reducing downtime. Second is it improves the reliability because I know all the parameters are working within the limits. For example, if I'm a human, I know there are certain parameters that has to be within the limit. For a healthy human, I can measure my heartbeat, I can measure my weight, I can measure my blood sugar level. These are the very basic parameter. If these things are within the limit and I can say that I am a healthy person, right? So by knowing the parameter, you can get reliability that this machine is working well. And lower maintenance cost. Why it is lower maintenance cost? Because the problem is getting solved even at the smallest possible stage. Since it is easy to solve small problem, low maintenance cost, and since I am able to take care of the machine, the life of the machine increases, which finally enhances the safety by preventing any catastrophic failure. All the points whatever we discussed are very much key point why a company actually interested in condition monitoring. Reduces downtime, improves reliability, lowers maintenance cost, increases equipment lifespan, and enhances safety. These are the five important points why condition monitoring actually matters. The next more important thing is understanding the maintenance strategies. See, there is a table that is given in front of you that is having a type, description, and applied. See, in the type, you see when there are certain maintenance will only come after the failure. For example, tire puncture. After the tire puncture only, I will change the tire. Not that my tire become very old. Now only I will change the new tire. No, I will wait for the failure. Then I change the tire. So such things are called as reactive maintenance, which means that once it fails, I will repair. There are certain failures are called as preventive failures, which means that I don't want some failure, so I have to prevent them. For example, brake. I don't want the failure to occur in the brake, then I have to repair. No. I will do a regular maintenance of the braking system so that I prevent the failure. Okay, so first maintenance strategy is reactive one, which is like maintaining after the failure. Second is preventive failure, which means that I don't want the failure, so I'm avoiding the failure. Third is predictive failure, which means that I have to predict the failure even before it comes. So this is a very good example is like your heartbeat. Once the heartbeat is in very good range, then you can say heart is good. If the range is slowly started deviating in time, then I know something is coming. For example, same one in blood sugar level, they used to take a 3 months average of the blood sugar. If the average is within 5.6, they say is healthy. If the ratio is going towards 5.6 and above, they say the person might get diabetes in future. So these are some predictive maintenance which predicts the failure. Same manner, some machine parameters using them we can able to predict. So there are three ways: either maintain after the repair, or prevent before the failure, or even predict the failure. This condition monitoring actually falls under the category called second and third. So I want to prevent the failure, number one, and also I want to predict the failure, number two. Okay, so there is also a very good saying in English that says that prevention is better than cure. So we try to predict and prevent, then to try to cure it through maintenance. Okay. Here, where the AI will be utilized, where the manual will be found, all the things we will be seeing in the upcoming slides. So what are the common parameters? We are always talking about I will take a parameter and I will check whether this parameter is within the limit. So what are the parameters? Say we are talking about condition monitoring of a equipment, which means that I have to make sure that all the conditions of the parameter that are needed for the smooth functioning of the component has to be evaluated. What are all the components? One is vibration, temperature, acoustics, lubricant, electrical energy, visual data. So vibration can be measured using a sensor called accelerometer. Usually when there is a misalignment or imbalance, then the body will start vibrating. How misalignment and imbalance can come? Due to wear and tear. When there is a too much wear on one side, so that side get imbalance, and there is a vibration that start to come on the rotating body. For the rotating body, vibration is a very good parameter to condition monitor. Okay, so how to do it? To accelerometer. Temperature, for example, if two bodies are touching and they are in constant movement, then definitely there is a concept called friction. How to avoid the friction? I put the lubrication. In fact, there is a component called bearing, which is majorly developed so that the shafts and the coupling can be kept so that your shaft and the housing of the shaft don't get frictions, right? But if the lubricant gets exhausted or lost in the operation, then temperature will start increasing. So temperature is a kind of parameter that says that the lubrication is lost and friction is happening. How to measure temperature? It's like thermocouple. And sound. Inherently, we know that sound is also a very good parameter to find the condition of a system. Say we are talking with our friend. Suddenly, if their voice is down, we know something is wrong. If their voice is very loud and happy, then we know he is fine. So this is the simplest example to understand that using the acoustics, we can know the condition of a system. But from the when you start a mixie daily, the sound we know how it has to come normally. Suddenly, if the sound is different, I know that my mixie motor has some issue. Okay. And now through the human ears, we can measure, we can hear it, but we cannot calculate the value of the sound. For that, we need a microphone or piezo sensor. And this acoustics can, the acoustics noise can also be created due to imbalance and misalignment. But cracks and leaks, for example, if there is a gas pipe and there is a crack, so the gas is getting leaked, sound will come, so I know there is a leak. If that is sound is not there, so I know there is no leak, right? And next is by measuring the lubricants, by analyzing the lubricants for the materials present in the lubricant, I know what is the wear that is happening and contamination that is coming. Say if the two bodies are rotating, for example, piston cylinder, let's take, because piston has to move inside the cylinder. So during that time, friction and wear and tear are created. To reduce it, I add a lubricant. So when there is a wear and tear, which means the particle getting scrapped away, will be falling in the lubricant oil. By analyzing the amount of particles in the lubricant, I know how much damage is happening inside it, right? Sometime and electrical current and voltage, it is like by knowing their consumptions, I know how much currents are utilized. And visual data, by looking at the crack which are visibly outside, I know there is a crack. So condition monitoring is not about science, it is about common sense. It is more like a common sense, because we are actually doing condition monitoring of our children even without even knowing what is condition monitoring. The mother takes care of the child. Through the crying of the child, mother knows what is the problem. So inherently, humans are trying to do condition monitoring, and only very recently we are putting it in the textbooks and making it as a new subject. And what are the steps? Technically, what are the steps? Say the steps are very simple. Step by step, we have to start from the lower steps and we will be progressing to higher stage. Higher. Typical condition monitoring starts from the data acquisition. So what is this data acquisition? Say, if you want to cause some good thing to somebody, or if you want to cause some bad thing to somebody, you need to know data about them. Without data, there is nothing you can do in this world, literally. All the social media softwares are giving their free account, are giving their free trial for collecting our data. So data is very important. So first step towards understanding how our machine works is to collect the data. What kind of data? They are the parameters data. We saw already vibration data, acoustic data, electrical data, or temperature data. And how the acquisition can be done? Through some sensors. So vibration data is collected through the sensors, and this is the data we have. Okay, so the first step is using a sensor, collecting the data. Once that is done, then comes the signal processing. Why signal processing is there? Data is already available. Use the data directly. Condition assessment? No. From outside, it looks like so easy to take the data and do the assessment. Actually, what we are missing is signal processing, because how pollutants are mixed in this atmosphere, how impurities are always present in anything, noises are present in the data. Now, instead of calling it a data, that technically I call it as a signal, because it is the signal I am receiving from the sensor. So any kind of signal, there is a impurity in the signal called as a noise. I'm calling it a signal to noise ratio. Okay, so every data, which means a signal, will have a noise. If I directly analyze them, then the data, whatever the result I am getting, may not be true because there is a noise. I have to remove the noise first. Then removal of noise and enhancing the actual signal is called as signal processing. Once I took a data and removed the noise, then I can go to the third step, that is condition assessment. Now, how to do condition assessment? I have a vibration data. Vibration data means it is a kind of sinusoidal waves. A simple sinusoidal wave may not give me any idea. So I have to extract certain parameters like maximum amplitude of the sine wave, frequency of the sine wave, RMS value of the sine wave. So these are the parameters that will be extracted from the signal, so that when these parameters are within the limit, they are fine. If they are not within the limit, then they are not fine. And based upon the value, I can even find out what is the possible problem that could have done. Okay. So I try to analyze the condition whether there is a problem or there is not a problem. Once the problem is identified, then I do fault diagnosis, which means what is the kind of fault I'll try to check, and that particular fault will be identified from the condition monitoring. And more importantly, if you cannot find the fault, which means that if you fail in fault diagnosis step, then your entire condition monitoring objective is failed. There is no use, let me go back, there is no use in doing data acquisition and signal processing and condition assessment when you don't know how to do fault diagnosis. So this is the very critical part. For example, if a patient is having a stomach pain, assume, so from the condition assessment, we can know something is wrong. So we'll send them from the X-ray or some kind of ultrasonic or whatever. So they take the data from that. They'll try to identify the fault. Then only they can. Then only they can give the diagnosis, and prognosis means treating them. So fault diagnosis, if you wrongly understand what is the fault, then the entire solution what you might provide will go wrong. Okay. So in the entire ladder of the steps, the very important critical step is the fault diagnosis step. Okay. So let us revise the basic steps. First is data acquisition. Very good. Signal processing, condition assessment, fault diagnosis, and maintenance. So these are very common steps in any kind of industry, not like mechanical, electrical, computer science. No, it's common for all. Okay. With that, we now, so far whatever we studied, we are only understanding what is condition monitoring and where is AI involved. A human can simply sit in front of the computer, can see what is the condition and can cross verify with the reference value and press red button for error, green button for good signal. But why AI will be utilized? And let's see the reason why AI can be utilized. The AI and machine learning transforms condition monitoring by automating the fault detection. Not only detection, after detecting there is a fault, they can diagnose. Diagnosis is possible. Further, from the rate of the data that is getting deviated from the normal, you can even predict using the pattern hidden in the larger data set. Human brain will have a difficulty in understanding the entire, uh, like in English we say connect the dots, because by connecting the dots sometime we may get the bigger picture, which is very difficult by the human brain. But when I train the AI ML, it can connect the dots easily and tell me and predict me what is the problem that can come. Okay. So now what AI can do? It can learn the complex nonlinear relation between the sensor signals and faults. Say if the fault is only one fault and the signals are affected by the fault, human can actually find. But if there is a combination of the fault, for example, crack, also loss of lubrication, then the both the signal of crack and loss of lubrication will combinedly come as a complex wave, which is very difficult for the human to understand. Okay, but AI can do for you. So especially when there is a combination of failures, and it also can detect anomalies in vibration or acoustic signals automatically. So AI actually calculates the data instantaneously. What is the data? Which means that there is a sine wave coming from the vibration. Each second RMS value will be calculated. Each second magnitude will be calculated. If the values are outside the range, immediately it will tell, which is done automatically. Okay, and this is the highest possible reason why you should go for AIML, because it can predict, or UL, that is in industry we call it is technically, it can predict remaining useful life of the component. See, in industry what they do is, I will take an example of my own project. In Coal India Limited, we are doing a project in which the mine started in 1951. Okay, 1951. Now it is 2025. It is more than 50 years. It's like 70 years plus. So now, in the beginning of 1951, they bought a new machine. They installed. Okay, and in next 10 years, less than 10 years, the mine, all the coals will be extracted. There won't be any coal left after 10 years. So the machine is already 75 years old. Now the Coal India Limited wants to know what is the remaining life of the components, remaining useful life. If the remaining useful life is more than 10 years, then there is no need to buy any new equipment, because coal is going to be there only for 10 years. So they will use the same equipment. After the coals are exhausted, they will discard the machine and go to next place to make mines. But if the remaining useful life is less than 10 years, then they need to find how to push them towards 10 years by reducing the capacity, or by some other means, by putting some external fittings, so that they don't have to do anything expensive, or they don't have to buy. So predicting useful life is highly needed in any kind of industries. So what we are doing is, we have taken the condition monitoring parameters and trying to predict the useful life by AI. Okay. And one more thing, what is very new is, continuously AI will have ability to adapt to the new data that is coming. Say, a machine can run at various conditions. So the signal is also affected by the conditions. If you are working on any kind of conditions, your data will be affected, right? So that data also has to be taken into account. So I cannot simply say a particular value of the sine wave is the limit, because that depends on what is the condition in which I am operating the machine. So the limit varies with the condition, which means condition at which my machine is getting operated. For example, when I am running the fan at a low speed and at high speed, the frequency of rotation is varying, right? Which means the signal it sends out from the machine also varies with respect to the operating condition, whether you are running at low speed or high speed, or it is loaded or it is unloaded. Okay, so all this different data can be instantaneously adapted by the AIML, which is little difficult for the manual people to adjust the conditions and adapt for the new condition. Okay, so now in traditionally AIML is not utilized. Let's see what is the benefit of AIML. Number one is, traditional condition monitoring is simple rule based analysis, but AIML is data driven analysis. So I will tell you what is rule based and data driven. For example, you are checking the Facebook and you are seeing the advertisement of a shirt. Okay, why it is coming in the Facebook, the advertisement of shirt? Because sometime before in Google you searched I want to buy a shirt, something relevant to that, so Facebook understood and then it is showing you the shirt. And you need to understand, these are not the simple yesterday's data it is utilizing to give you the advertisement. It is studying your data for last 1 month. For example, the video recommendation, the reels, whatever it is coming are based on the 1 month data. They take the too much data, what are the kinds of reels, what are the kinds of topics you are watching for last 1 month. Through that, it creates the model. Same manner, a machine, what is the behavior of the machine along a long duration? Using that, it can find the fault. But the traditional condition monitoring does not take the history of the machines. It simply takes the instantaneous value, compare with the limit. If it is less than the limit, machine is working fine. More than the limit, machine is failure, it will tell. But sometimes there are minute details in the failure that are hidden inside the limit. For example, I set the limit as 100. Anything less than 100, claim safe. More than 100, claim unsafe. Okay. So the slowly the magnitude is starting from 70, 71, 72, 73, 74, 75, 80, 85. So your traditional system will say safe, 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 and it will never understand that the magnitude is actually growing. And once the magnitude touch 100 and 101, then only your traditional system will say the machine failed or machine is not working properly. But AI driven will understand that magnitude is slowly increasing even before it touches the 100. It will see from 70, it's slowly increasing to 80, 85, which means there is something, definitely there is a problem. So it will tell you the problem, which is not possible or not that much made to do with the condition monitoring in traditional systems. Okay. The second important is fault detection. When there is a fault, usually in condition monitoring of traditional system, you need an experienced person to tell the problem from the data. See, some people by hearing the noise in the rotation only, they will tell whether problem is on the magnet or on the stator or on the wiring or on the windings. But if the experienced person is not available, then for the newcomer, it is very difficult to predict. But AI is not that way because AI don't utilize the expertise, but it is utilizing the automated patterns. The patterns are already incorporated in the program, and then boom, it can find the fault without the need of an external expertise. And second is adaptability. What is adaptability? For example, I designed a condition monitoring system to find only crack and lubrication loss. So traditional system, I have made it to find only crack and lubrication loss. So it will only find these two. But assume suddenly in future misalignment started coming, your traditional system cannot adapt for the new error, cannot adapt for the new problem. But AI is not that way. Once the AI learns the signal, whatever coming, is not matching with the crack behavior nor matching with the lubrication loss, but a new kind of signal is also coming in it. So this AI will alert the user that something is actually happening which is not intend to happen. Okay, so it will learn from the new data. In future, it will also predict the leakage also. And misalignment. Okay, so these are the new adaptability AI can do, and the prediction. Uh, as I told, AI only can predict remaining useful life. Your traditional condition monitoring can never predict. It only can check as of now what is happening. Okay, so these are the very major things that are happening. Now, what are the data a condition monitoring system utilizes? We already saw condition monitoring relies on the sensor data, okay, from the machines, and how these data are connected with each other, which is called patterns, to detect the anomalies. Okay, so now let's see what are the actual data and how they are done. We already saw earlier, but let's say a little detail. So for AI, because it is based on AI, so what are the data that is useful for AI? Okay, that is what we are going to focus. So first is AI also uses the vibration data which is taken from accelerometer. So vibration based condition monitoring is one of the very common method for rotating objects. Rotating objects like motor, generator, engine, any big machine which is having a rotating shaft, this vibration data is very useful way to find the condition. Okay. The next is acoustics. AI also utilizes the acoustic data. Okay, so using acoustic data, AI can detect many things. And AI also uses temperature data. As the temperature fluctuation is observed, it can tell what is happening. And lastly, and nextly, voltage data. By understanding how the voltage is happening, for example, your phone. If you charge your phone, always you know the charge will be available till evening. Like if I charge my phone 100% in the morning, my charge will be available till evening or night. But suddenly in the afternoon only charge gets over, which means that from the voltage data also I can know there is something wrong, because always my charge remains till night, but suddenly my charge gets over in the afternoon, which means that something is not correct with my phone. Either phone may some software is running which is consuming the battery, or some part is not working, so that large amount of voltage is utilized. Okay, so this one example where voltage data is very much important. And the next is lubrication data, wear and tear we already discussed, and pressure data. Because pressure data is very much useful data for the leakages. Because when there is a leakage, there is a loss of pressure. And one thing we need to understand, there is always loss of pressure whenever there is a flow of gas. The loss of pressure may come from leakage. The loss of pressure can come due to the friction between the fluid and the pipe. Okay. So loss of pressure always comes. So this pressure data is also useful to understand many things like leakage and also the flow and the flow velocity. Many things you can find from the pressure data. And lastly is visual data. For example, drones. When the drone is flying near the Indian border, using the infrared radiation, they can predict the presence of an unwanted persons, right? So such things are possible by simply looking at the object and identifying what is present in the object to give the conditions. So from the machine, sometimes the vibration of the machine is clearly visible, or some external cracks are clearly visible. Okay, so these are the data that are collected based on the sensing type or sensors. So AI, is it using only this data? No, because these are, for example, vibration data maybe is usually collected in time domain, which means x-axis is in time, y-axis is the amplitude of vibration. So vibration data is collected generally in time domain. So let's see based on the nature how data are collected by the AI. The AI collects the data based on time domain analysis, which means based on time domain or frequency domain or time and frequency domain or operational data or image data. The time domain data is the common data format for vibration, because vibration signals in practical life is coming as a time domain only. Okay, so the raw data is in time domain. We can easily identify them. Frequency domain data is also taken for vibration data, so that we can identify what are the specific frequencies present in the data that can enable us to find many things. We will see some one or two examples how to do, but let's understand what are the various data first. Second is time frequency data. So this is using both time and frequency, which means that it is a three-dimensional value. Y, which z, that is vertical up is the magnitude of any parameter along x and y. One axis will be in time, other axis will be in frequency. So the time frequency domain is utilized to merge the advantage of both time and frequency domain. And next is operational data, like what is the load it can take, what is the time it takes to run, so operational data, and finally image data which is there. So based on the type of data, sensing data, we saw what are the different kind of sensing. Based on the nature data, we are seeing what are the nature, and last type of data is based on the collection level. A data may be collected at the component level, or data may be collected at the system level, or data may be connected at the plant level. The component level means it will give the detailed information about the component. For example, bearing, bears like bearing, gear, and shaft, many other things. System level means instead of keeping it on the bearings and the gears, I'm going to keep it on the pump and motor, it's on the overall component. Okay, plant level means I'm going to keep it on different locations in the plant so that I'm getting the overall idea of the health of the entire plant. Okay, so these are the collection of data that are taken care by the AI. See, the AI and the condition monitoring steps are very much literally same. Always every condition monitoring starts with the data acquisition, and what are the different kinds of data that AI uses we already saw. Okay, now we need to understand what is the algorithm that identifies and analyzes these data. Okay, so the general thing is like AI models are supervised learning, unsupervised learning, semi-supervised learning, reinforced learning, and deep learning models. So the goals and outputs are already given. You can see supervised learnings are very good for fault classification and RUL, remaining useful life prediction. Unsupervised learning techniques are useful for anomaly detection. Semi-supervised learnings are useful for identifying small labeled and unlabeled data. And reinforced learnings are good for prescriptive maintenance and decision making. Deep model is advanced version of all. Okay, so it's like end-to-end pattern recognition is possible. So it might sound little complicated, so I have made it in a very simple takeaway. Supervised learnings are good for finding the faults. Unsupervised are good for finding out anomalies. Deep learning are good to extract data, and reinforced learnings are good for optimizing the maintenance action. Finally, hybrids are better for everything, which means you can mix them all and find out. Okay, what kind of AI model you might use actually, and determined by what you want to finally do with the system once you identify what is the problem. Okay, so now let's see one simple diagrammatic representation of what is vibration based condition monitoring. As I told, vibration based condition monitoring is one of the common and most used method for rotating machine. So let's see two cases, normal machinery and abnormal machinery. See, when the system is completely rotating, there are so many signals coming from each part of the machine. For example, you can see from 3 points, the machines are coming for the normal, and finally in the composite wave, they are all added together. Okay, but in the abnormal, assume that in the middle shaft, there is a problem. So what is happening? The other two signals are not disturbed because these two parts are working. Only the part which is having the signal will have a different signal. In that, finally, your output signal will look like this. So by looking visually only, how the healthy signal generally looks, how the signals of the abnormal one, you can easily predict there is abnormality. Okay, so where in each dot there is kind of accelerometer that is kept in each location. so that I know the signals individually, and finally I will get the composite waveform. Okay, so that composite waveform is useful to identify what is the failure. Now, vibration based condition monitoring is very clear, I hope by now. Now let's take an exact example. It is like industry example to see how AI is useful in the condition monitoring. So let's take an example of a crack detection in bearing using vibration based AIML condition monitoring. Okay. So by using the AIML condition monitoring, I am going to predict what is the cracks that are coming. So as you know, bearing rotates very smoothly because it is designed to rotate very smoothly. So its vibration is predict periodic and stable. But when crack develops, smoothness is disturbed. Due to that, there is a localized impact because there is a crack. The system will have a localized impact, and it will also have a repetitive shock impulse because it is cracked, and that will give side bands and harmonics. You don't worry right now what is this side bands and harmonics. It is the frequency domain parameter which will be evaluated from the frequency domain results. So if this condition monitoring is a very generalized topic, right? So I did not tell much of the details of time and frequency domain, but I have given enough knowledge on how to customize in applying the condition monitoring. So we have taken the specific for crack detection and bearing. So the side bands and harmonics are the new parameter that will appear in the um, in the frequency domain. See, what is this harmonics? I hope I can use the mouse and try to explain. See, for example, if in frequency domain, if the entire machine is running at 1000 RPM, so in the frequency domain, there will be a peak that is coming at the 1000 RPM. Okay, that will come at the 1000 RPM. 1000. But when there is a crack, then they are saying there are harmonics. Harmonics means again in the multiples of 1000, like in 2000 also you will have a peak, in 3000 also you will have a peak, in 4000 also you will have a peak. So previously you had only one peak in your system, okay, but suddenly you will see so many peaks which are harmonics, which means that in the multiple of the basic frequency, that is called harmonics. What is side bands? Side bands are nothing but, if this is your curve frequency in FFT, if this is your frequency, you will have one more peak in this side and one more peak this side. In the they also will be in harmonic, but there will be a peak on both the sides. That's why it's called side band. Okay, there will be one peak, but you see previously there will be one. This is the healthy one. For example, this is the healthy signal coming at 1000 RPM. That peak would be coming here at 1000 RPM. But here the same peak will be in 1000 RPM, but inside there will be two more small peaks. Okay, two more small peak. For example, if this is 1000, this is like 700, one peak will come, 1300, one peak will come. Exactly even manner, both peak will be there. Okay, this peak will be in 700, this peak will be in 1300, and this will be in 1000. So in 300 RPM difference, there will be a peak. So these are the different kind of signals that would come, using which we can able to measure. But now let's see how we will measure. Now let's go to. Okay. Now we have to have to get the data, which can be done through the sensors. Like you see, there is a shaft rotating and there is a bearing, and I have kept the accelerometers here, one, and I've kept the second accelerometer here. So these two accelerometers are getting the signal. So they are like piezoelectric accelerometers mounted on the bearing housing. The signal type is a time domain data will be collected by them, and I am using a sampling frequency 12 kilohertz to 48 kilohertz. What is the sampling frequency? It is a very important uh, specification of the sensor. It is better to have a sampling frequency as high as possible. Okay. So because higher sampling frequency can detect even the smallest cracks. So I will always go for a sampling frequency of the sensor, which is either between 12 to 48 kilohertz. So once the data collected, what are the things we wanted is, we need to know what is the healthy bearing data. We also wanted the bearing with the small crack data, bearing with the severe crack data. So when I want to use this I need to know, or I have to teach AI how a bearing with the small crack would give data, how a bearing with a severe crack would give data. They are like fingerprints. That's why I have added a fingerprint. They are like a fingerprints. You don't change. A normal bearing gives a signal. Okay, it always gives same signal. Under a same condition, a normal bearing always give same signal. So you need to know how your bearing will give signal for the different working condition. Now the same bearing, if there is a small crack, how they will give the signal, you should actually experimentally do and get the signal. And you also need to have how the bearing will give signal if it is there is a severe crack. Because these are input data which is needed to train your AI model. Because AI is also like a human. If I recruit a new person, he also don't know anything. When I make AI program, it also don't know anything. So I have to train a human the same way I have to train a AI by providing the healthy data, already cracked data, already severely cracked data. Same way human also shown how the data would look on different scales, right? So I have to train my data. Once the data is trained, since I am supervising the learning, it is coming here as supervised learning because I am training my data. So the kind of AI what I will use is supervised learning. Now, this is one simple example of the data I have shown on different conditions. Like, no, where is my mouse? Okay. This is like a no load condition. This is like unbalanced condition. So I have to experimentally get the 1 minute. I will erase. Wait, no, no. Array, how to make it big? Okay. So now let's not worry about 1 minute. Erase all in this side. Okay. So now there is a no load condition, there is unload condition. This data, whatever I experimentally got, right, this complete data, whatever I got experimentally will be the input given to the AI already, so that my AI know how the no load condition, experimental load condition will be working. Okay. And assume this is the data received by the AI in the working condition also. So what it does is, using the time domain parameter, it calculates the root mean square. What is the root mean square? For any sine curve, I can calculate RMS value. I can calculate peak to peak value. I can calculate the kurtosis. I can calculate crest factor. I can calculate skewness. You don't have to worry about this parameter. See, when I am using a time domain parameter, there are certain uh, key values which you can calculate. Those values are kurtosis, crest factor, skewness. So these are the values I will calculate from the time domain data to understand the presence of the failure. Say from the root mean square, the root mean square value will be increases due to the presence of crack. So I will be calculate RMS value. Suddenly RMS value start increasing, which means that there is a crack. Peak to peak value will also be increasing, so that shows the crack is there. Kurtosis also will show a sharp rise. Crest factor is also shows a sharp rise. Skewness also shows a highly irregular waveform. So all the different parameter is pointing out that their values are keep increasing. Okay. So if it is a crack, all the parameters of the time domain will show a sharp increase and they increase with time. But this kind of behavior is not always shown. For example, for misalignment, the combination might give different kind of data which your AI has to be trained. But since it is a crack, all the parameter increases, and now my AI will understand this is the a crack that is coming. And also, in frequency domain, it calculates what we called as ball pass frequency of outer and ball pass frequency of inner on a normal condition and on the abnormal condition. And it also looks for the side bands. As I told you, until there is no side band, then there is no crack. Appear of side band gives the presence of crack, and also it checks the high frequency resonances, which means that I can say the resonances high frequency in the sense the harmonics that are coming up. So these are all the datas are used. It's not only one data, two data. All the time domain data, all the frequency domain data are instantaneously calculated for a given duration of the window to come to a conclusion called this system has cracked. Okay, so you can understand from this simple example, the AI predicts crack not from the one data, but by using the various combinations of the data, and all the data are collectively calculated and studied on their pattern to say what is the failure. Okay, when all the data are increases, it means cracked. There are cases for other failures, some data might increase, but some other data might decrease. Okay, so you need to know what increases, what decreases, the pattern. If you understand, it can detect the failure. Now, what are the steps actually AI is using? It's very simple. AI first gets the data and do what we called as a pre-processing. After the pre-processing, it extract the parameters, whatever we studied, the statistical parameters like RMS, kurtosis, okay. And after taking these values from the healthy one, it uses the support vector machine or random forest models to train so that it can understand what is healthy and what is cracked. Cracked means whatever it may be, whether it is cracked or any kind of failure. So first is data collection and pre-processing. Second is data extraction and learning and comparison between both. The third is model training and validation. Whatever data it calculated in the real time, it takes the data and compare it with the pre-program so that it can understand what is the output, and finally a result would be coming like this. For example, this is the input parameters we have given to them, like if RMS of the healthy would be lying like 0.85. If it is 0.42, 0.85 means minor crack, 1.55 means severe crack. Kurtosis 3.1 for healthy, 6.7 for unhealthy, 11.4 for severe crack. So that you see all the values are increasing. So that increase in the RMS value in the system shows that the probability of prediction is actually growing from 5% to 98%. Okay, so which means that the healthy one, the prediction of crack is very less, but slowly when the values are patterns are observed, the prediction of the crack starts coming. And now what is more important to understand is AI can see pattern in vibration data that human eye or FFT alone cannot, enabling earlier and smarter fault detection. So this is very much important. That's why we are trying to say AI ML is highly needed. But AI ML right now is a fundamental knowledge that every human should know. Why you should left out of the AI? AI is used for everything. Why we have to left out? And here, in the next section, we are going to see one specific topic of my own research to show what is the new AI-based method we have developed. That would be more interesting also. Before going into the next section, I wanted to have one point so that condition monitoring how important it is. The condition monitoring is not only needed for the component, it is also needed for our children's. See, we need to monitor their conditions, what they are doing, when they are sleeping, when they are waking up, when they are going to school daily, when they are coming back from the school daily, what is their behavior of them daily at home, what they are eating, when they are eating. As a parent, we need to observe the conditions of the children's, what kind of dresses they are wearing, what kind of habits they are following. Because if you monitor the conditions daily, you don't have to tell your children that I am monitoring. But as a parent, I want to make sure that my own child actually performs better in life without getting spoiled in the society. So that once I start monitoring the conditions, once you observe there is a change in the condition, you can know that something may be wrong or something may be right is happening. If the change is positive or change is negative. Okay. If negative changes are happening when compared with the daily routine, then there is something that is not appropriate for their future is happening. But if the change is positive, then you can understand they are in the right track. So condition monitoring is not only fixed to the what you called missions. It is also needed for every parent so that their children's future can be secured healthy manner. Okay. So now let's go to the gear fault diagnosis that we created in our own lab. So you can see it is like it was done by ourselves in the lab, and it got published also. The paper where it is published is given here, and my name is here. So now here what we did is we developed a new technique to detect the failure. The new technique we followed is called visibility graph. So this visibility graph do not calculate kurtosis or RMS value or anything. It follows the concept called network theory, in that especially called visibility graph. Okay, let's see what it is. See, what is visibility graph? In order to understand, you can easily say, see how far you can see. Visibility means what? How far it is visible. How far you can see. For example, the peak number 1, due to its height, it can see peak number 2 and it can see peak number 3. But from the height, it cannot see peak number 4. And peak number 2 can see peak number 1, can see peak number 2. From its height, it cannot see peak number 4. But peak number 3 can watch 1 and 2 and can watch 4. Same way, peak number 5 can watch peak number 4, but it cannot watch peak number 1, 2, and 3. And peak number 6, same manner, every peak can watch other peak depending on their height. This is called as visibility graph. So I will be creating a visibility pattern. For example, for pattern 1, for peak 1, the visibility numbers are 2 and 3. And for the peak number 2, the visibility numbers are 1 and 3. Suddenly you understand the visibility of 2 also becomes 3 and 4. Okay, what is the meaning? In regular times, the peak is only visible 1 and 3. But suddenly if 4 is visible, what is the meaning? The meaning is the magnitude of the 2 was actually increased. When magnitude of 2 is suddenly increased, then amount of peak it can see becomes 1, 3 and also 4. And after 4 it cannot see because all others are behind it. Okay. So based on the patterns, based on the visibility pattern, I can know is there any sudden change in the visibility pattern so that I can predict the failure. Okay, this is called visibility curve. For example, for 8, let's see for 8, the visibility patterns is that it can watch 7 and it can watch 9. But think suddenly it can watch 10 8, 9, and 10. What is the meaning? Meaning is 8 has grown to height above 9 also, so that it can watch 10, and also it can watch now 4, it can watch 5, it can watch 6. So suddenly the pattern, what are the peaks it can see changes. Okay, so this is utilized to find there is sudden increase in peak or not. Okay, so this is the signal of data points. You can see at a 20 hertz speed at zero torque. 0 volt means zero torque, and 20 hertz speed. We give the input of healthy, chipped tooth, missing tooth, root fault, and surface fault. Each pattern is, this is for healthy, this is for chipped tooth, this is for missing tooth, this is for root fault, this is for surface fault. In each category, the relations visibility patterns of each peak is created by the AI program. Okay. Now what happens? Using this as for each peak, the visibility pattern will be noted down. So when the machine is running, what is the patterns of the each peak at this same condition at the same data points? If the pattern is same, then it is healthy. If the patterns are not same, then there is a problem. And by our analysis, in fact, we proven in the research paper that we were able to predict 100% success for the healthy system when it is running at 20 hertz and zero torque. But at a 30 hertz and 2 volt torque, our accuracy is only 96. We were able to predict the chip tooth 100% at zero torque, missing tooth 95% accuracy, 98, 96, 98. And of course, at high RPM, the percentage is slightly reducing. But what is the point we wanted to make by the understanding is, we were able to actually predict the failure without calculating time domain or frequency domain parameter, but getting the visibility pattern of the system. Okay, so these are the various way in which your AI can be utilized for condition monitoring, and how you can help the industries to grow higher and higher, and they're down without going into the downtime, so that the profit and production can be very much high. Okay, so with that, I would like to finish my content. So I hope I have given you an overview of what is condition monitoring, what are the parameter, how AI start coming in between, and how AI actually finds it, and how AI can help you to find the fault. And there is a real-time example of a new AI which is different from all the traditional AI, and not even utilizing any of the parameters, but by using a new concept. This concept, I want to make one note that whatever we have used is not the end of our research. Please read the paper. Like for example, you can note down the title of the paper. It is available in Sage. This work, we have only told the possibility of a new technique. Now this can be applied to bearing any kind of failure. We only used gear fault. Okay, now same technique can be applied to bearing failure or any other component failure, and new paper and new research can be published. The entire methodology is given in detail, and we also got appreciation from the journal for these findings. Okay, anyway, with that I finish my content, and if you have any queries, you can always mail to me. My mail ID is given. Okay, thank you. Hey Bhargav, yes, thank you very much. I finished my talk.
Thank you, sir. Dear participants, do you have any queries? Yes, dear participants, any queries? Vibration isolation. Sir, hello, sir.
Yes, yes, please.
Here, our committee members are just requesting to discuss about that vibration isolation and negative stiffness of that what we have done in the lab.
Mm-hmm.
Just because
Okay, okay.
yesterday people were interested in metamaterials, they were asking questions to Sahu sir on metamaterials.
Which Sagar? Ranjit Kumar.
Our Ranjit sir. Yes.
Okay, okay.
So if you can just
Okay. How did they find I working on this field? Matlab, you
no, no,
told.
I told, sir. But
Okay.
actually, yesterday in the discussion, I just informed that in our lab also we are working on metamaterials like that.
Hmm.
So in that scenario, so Samir
Okay.
sir is asking just to give some 2 minutes.
Okay, okay. That's actually a very interesting topic, actually.
Yes, sir.
See, very straightforward. The only thing is I'm not having slides to present, but I'll try to utilize it. See, let's take a simple cantilever. Okay. So when I try to apply a force, my cantilever will resist the force. Okay. My cantilever actually resists the force. So that resistance against the force is what I'm claiming as a positive stiffness, that is like straight line. Okay. It looks like curve, but it is straight line. So that is the positive stiffness. But if the cantilever reaction, okay, the reaction, what is Newton's third law, like action and reactions are, for every action there is a equal and opposite reaction. The reaction should be against my action. If that is happening, then the system is having a positive stiffness. But under certain conditions, the reaction also will be in the same direction of action. Okay, under certain condition, the reaction is also in the same direction. For example, my force is downwards, my reaction is also downwards under certain condition. So that time, my system actually, what kind of stiffness it is representing is a negative stiffness. Okay, so the negative stiffness will be exhibited in the system when the reaction of the system is also in the same direction to the applied load. And does that mean it is violating Newton's third law? No, it is not violating Newton's third law, because the understanding can be given from the stability point of view. See, now I can explain which condition that is giving. For example, I am taking a arch. Okay, I am taking a arch and I am applying a force from the bottom. Until the certain vertical displacement, my reaction force will be uh, against the applied force. So it will exhibit a positive stiffness. But once I compress to certain distance, immediately it is buckling downwards to the other direction. So in the period of buckling from this to this, the reaction force also will be downwards, the action is also downwards. So the sudden buckling, sudden snapping, I can say the sudden snapping is represented as the negative stiffness. Once it is snaps towards downward, the further forward force is acted against by the reaction. So again you start getting the positive stiffness. Okay, so the region in which you are getting the negative stiffness is due to the snapping mechanism. You know, the young people are playing with the bubbles. Like there is a bubble wrap game. When they will press the bubble, it gets flips to the downside, and from the downside they press, it flips to the top side. Okay, so the arch kind of mechanism is having a two stable state. One is the first stable state, other one is the second stable state. So when I press vertically up to certain displacement, it snaps from first stable state to second stable state. It is just shifting from one stable position to another, right? So this is what we are calling as a negative stiffness mechanism. So this negative stiffness is actually useful in many applications, because so far they were thinking everywhere I need positive stiffness. But in vibration application, we are more interested in a concept called zero stiffness. See, every system has some kind of stiffness. There is no system in the world as zero stiffness. But in vibration isolation, I would be more happy to have a zero stiffness. Okay. But how to get a zero stiffness? See, this is the negative stiffness. So assume it is a minus 10. Okay. So how to make this minus 10 into 0? That is by adding positive 10. So if I add the combination of negative stiffness and the positive stiffness, the slope of this curve, okay, would become like this: positive stiffness, and the negative region will become flat, and again you get up. So there's the region where both negative and positive counteracted is will have a zero stiffness theoretically. Okay, so this zero stiffness region is used in vibration isolation. So such the system which exhibits such a nature of the curve is called as quasi-zero stiffness structure. Okay, so in fact, you could have requested me to present topic on vibration isolation or QZS. I would have told much more in detail, but to keep it crisp and short, I can say so how the positive and negative stiffness are combined. I will show the a simple diagram. See, this is the arch. Okay, the individual arch will have a negative stiffness, but I will add a
This is
positive stiffness.
sir, video is not visible.
Are my God, are okay. Bhargav ji, you could have told me before.
No, actually, the
I,
words were means we could have understood with the words. Now, when you said that you are showing,
oh, then only you understood. I did not.
yes.
Actually, I have stopped sharing my screen and I started drawing structures. Okay, but anyway, no problem.
Sir.
Uh, okay, I will quickly draw it in 1 minute. It's again like a simple. Can I just drawn only one thing? Can you see my screen?
Yeah, yeah. Now it is visible, sir.
Yeah, you see, this is the cantilever, and I am applying a force. Okay, from the downwards. So the reaction force from the cantilever will be against my force. So this is called a positive stiffness. When I draw force displacement, assume this is line. Okay, it is coming like a curve, but line. It will have a positive stiffness. But when the reaction is also towards the force, then I will have negative stiffness. This is what I call this. Okay, this kind of situation can occur to a curved structures where there is a curve which is fixed at both end. Okay, so when I try to press from the top until the certain vertical displacement, my reaction force will be against it. So I will have a positive stiffness. But after a certain vertical displacement, it immediately snaps down. During the snapping, my reaction force and positive, my action are in same direction. So I get a negative stiffness region. But after it snaps down, my action and reaction are against opposite to each other. That I'm getting as a positive stiffness. Okay, so this is the negative stiffness region that is coming because my object snaps from one stable state to another stable state. Now I want to make a QZS by adding, for example, if this negative is minus 10, uh, so okay, so this is like I want to make a zero stiffness region by adding a positive 10. So then how it is physically? Okay, so this is the arch. To the arch there is a spring. Okay, this actually it is a spring. Okay, assume it is the spring. The stiffness of the spring is exactly same as what is the negative slope. Okay, so when I apply the force displacement curve of a arch supported by the spring at the middle will get the force displacement curve as positive and zero stiffness and positive. So this zero stiffness region is utilized in the vibration isolation because to keep it in short, In order to get a better vibration isolation, my fundamental concept is I have to reduce my natural frequency below the excitation frequency. For example, if the excitation frequency is 100 hertz, okay, my natural frequency should be less than 100 hertz. How much less I am taking, that much better vibration isolation I will get. So if the excitation is 10 hertz, then I have to reduce it below 10. Okay, for example, I kept the frequency natural as 50 hertz. When the excitation is 100, my body will isolate. But if the excitation is coming at 10, which is greater than 50, so then it is 50, but you are getting 10, which means that my natural is more than excitation, then isolation will not happen. So then what happened? I have to keep reducing. But instead, if I keep a zero natural frequency, then what? Because frequency can never be negative. It starts from zero to positive. So if I have a zero natural frequency, that is the lowest possible natural frequency, then my system is isolated against any kind of excitation, which means that I don't have to worry about what is the incoming frequency that is coming because I'm already kept my natural frequency zero. Okay, so what is the concept? Reduce the natural frequency below the excitation. How much you can reduce? Let's make it zero. So that any frequency that is coming is always 1, 2, 3, up to any number is always greater than zero. My system is always isolated in that range. Okay, so this is a one small overview about quasi-zero condition. This is the curve that is coming is called as QZS, that is like quasi-zero stiffness, QZS. Why quasi-zero? Because zero stiffness is only available in the small region, so it is called as quasi. Quasi means only for a short region. Zero stiffness. Okay, is it fine, Bhargav? You can ask them if they have any query on this.
No, sir. It's fine, I think. Dear participants, do you have any queries? Okay, sir. I hope there are no queries.
Okay.
Thank you, sir. Thanks a lot for the presentation. Nice presentation. And also, you again discuss the quasi-zero stiffness for us. Thanks a lot.
Okay.
Thank you for your valuable time, sir. Thank you.
Okay, man. Thank you. Thanks for this opportunity. So shall I leave?
Yes, sir. Yes, sir.
Okay.
Thank you.
Thank you.
Thanks a lot, sir. Dear participants, we'll have